Okay. There we go. All right. So we're going to start by taking a look at page 52. Okay, page 52. And we do not want to be doing chemistry 12. That's a little terrifying. All right. There we go. So if we go to 52, these are looking at chemical properties or physical properties. Remember, if it's chemical property, that's how it reacts. So unless it's talking about how it's reacting, it's going to be a physical property. So blue. Blue is physical, P. All right, so you guys just say P or C as we go along, and then we're going to talk about some of the ones that might be a little weird, okay? Hexagonal crystal structure, P. Flammability, how well does it burn? C. Solubility, how well does it dissolve? P. And that's because if you take salt and you dissolve it, it's dissolved salt. It's still salt. And what's happened is we've taken salt. What does it mean if I write an S in brackets? An S in brackets means that that salt is what state? Solid. Whoops, not sold, solid. Now, when we dissolve our salt, what state would that be? Are you off on a field trip? Yeah, okay, see ya. Do you need to go? Yeah. What state is the salt if it is dissolved? That is aqueous. So dissolved salt is aqueous. Anytime we have had a change of state, okay, so going from solid to aqueous, that's a change of state. Anytime it's a change of state, that is physical. So that one's a little bit complicated. When we're dissolving things, sometimes it looks like we're getting something new, but we actually have not gotten anything new. All right. Next one we have reacts with acid to form hydrogen. C or P? Reacts with acid to form hydrogen. Number 5, C or P? C. Supports combustion or burning. C, because burning is a chemical reaction. Melting point, the temperature at which its substance melts. That's physical because we are changing state. If we are melting, what state are we changing from and what state are we changing to? we're changing from solid to liquid. Okay, and remember that's my L, but if you want to write a regular L, that's fine. Okay? Malleability. How many people have heard the word malleability before? Okay, it is one of the vocab words that you're going to be responsible for. So I'm going to put a red box around it. I'm going to put a star beside it. And I'm going to highlight it. And don't worry, we'll come across it again later as well. Malleability means it's going to deform if you hit it with a hammer. So imagine that you are a blacksmith, yes? And you've got a piece of iron, and you're like hammering away on that iron. Is that iron going to shatter, or is it going to just deform a little bit? It's going to deform. Metals are malleable. Metals are malleable. And this is one of the ways that this particular section ties in with the periodic table, because on the periodic table, you are going to be able to recognize which elements are metals and thus are malleable, and which elements are non-metals and thus are not malleable. Ductility is the ability to be pulled into wires rather than snapping. Anyone heard the word ductile before? Okay. Who was your teacher last year? Miss Sambal, good for her. Good job. Unless you heard it elsewhere. Well, good job, Bill Nye. Excellent. Okay. Ductile means it's able to be pulled into a wire. And again, that's going to be a vocab word for this unit. Metals are ductile. Now, we didn't actually write down whether these are chemical or physical. If you hit something with a hammer and it changes its shape, if you hit something with a hammer and it changes its shape, is that a chemical change or a physical change? Physical. If you pull something and it goes into a wire, is that chemical or physical? Physical. Excuse me a second. Okay. Now, the opposite of malleable is brittle. Brittle is another vocab word. Brittle is the opposite of malleable. So if malleable means you hit it with a hammer and it deforms, then what does brittle mean? If you hit it with a hammer, what's going to happen to it? It's going to break, okay? Non-metals are brittle. Is that a chemical or a physical property? If you hit it with a hammer and it breaks, physical. We have no new substance forming. And density, the amount of mass in a given volume, chemical or physical? Physical. Okay, and those are our three vocab words. Let's head on over to a sour taste. Chemical or physical? Physical. Reacts with water. If you see that word reacts, that tells you it is chemical. Hardness, physical. Shininess or luster, physical, because it's not about how it's reacting. Odor or smell, physical. Again, it's not reacting. Reacts with air, that's chemical, because it's a reaction. And then finally, boiling point. At boiling point, what change is happening? We are going from what state to what state? We're going from liquid to gas. And what do we call that process? Liquid to gas. Evaporation. Or, in this case, you could actually say boiling. Evaporation is when it happens at room temperature. Okay, because water will just evaporate at room temperature. But if you actually heat it to its boiling point, then that's at the boiling point. Did we have any chemical change there? So if I take water and I boil it, will I get something different than water, or will I still have water? I'll still have water. It's just going to be water vapor. So that's going to be a physical change. Okay, good stuff. All right, let's go through these next ones. On page 53, table salt dissolves in water. Chemical or physical? Physical. What state was our table salt? Solid. And what state did it change to? Aqueous. What's an aqueous? An aqueous means, it literally just means dissolved in water. Okay, and so our four states then that we're going to be worried about this year are solid, liquid, gas, and then our fourth state that we're worried about in grade 9 is AQ, which means dissolved in water. Okay? Good question. Silver tarnishes. Sometimes people don't know what tarnished silver looks like because nobody has actual silverware anymore. Does anybody have silverware, like actual, so you got some silver? What happens to it if you let it sit for a long time? It gets like this layer, like if this is your piece of, if this is your piece of silver, it's all shiny and silvery, yes, but on the top, it'll get like a black coating on it, okay? That's what happens when silver tarnishes. We get a black coating. That black coating is a new substance. And if that's a new substance, is that a chemical change or a physical change? Anytime we get a new substance, that's always going to be chemical. And in fact, what's happened is that you have had silver, it has reacted with oxygen in the air, and you got silver oxide, and the silver oxide is black. You don't need to worry about that reaction, okay? But you did get a new substance. You started with silver and oxygen, and you ended up with silver oxide, which is a new substance. An apple is cut, chemical or physical? Physical. Heat changes water to steam. Physical. Baking soda reacts with, I should say with, vinegar. I need to fix that. And I put vinegar, my goodness. Vinegar. This note is for me. I need to fix that because it looks silly. Chemical. Iron rusts. Chemical. Because you end up with a new substance you did not have rust before. Now you have rust. It's a reaction very much like silver tarnishing. In this case, iron is reacting with oxygen, and you get iron oxide, which is rust. Alcohol evaporates. Chemical or physical? Physical. Ice melts. Physical. Milk sours. Chemical, because we didn't used to have the sourness and now we do. That's a new substance. Sugar dissolves in water. Physical. What state did we start with? We started with solid. Sugar is solid, and we finished with aqueous. Good stuff. Wood rots. Chemical or physical? Chemical. Pancakes cook. Chemical. Because we used to have liquid batter and now it's solid and you can't get it back, and yeah, that's chemical. How about grass growing? It's actually chemical, because what you have is you have photosynthesis, making new plant bits. Okay, you got CO2 plus H2O is C6H12O6 plus O2. You do not need to know this. No, absolutely do not need to know it. Okay? But what you should know is that the new grass molecules are being produced by chemical reactions. And you do not need to know the photosynthesis. What if we inflate a tire? Is that chemical or physical? Physical. If we digest our food? Chemical. A paper towel absorbs water. That is physical. Okay. And now let's go to 55. By the way, was anybody interested in knowing what an intensive and extensive property are while we're here? You're interested? Okay, just very quickly on page 54, an intensive property, because this is an enriched sort of a thing, and an extensive property intensive does not depend on the amount. So if you have color, does the color depend on the amount? No. Does taste depend on the amount? No. Ice is going to melt at the same temperature, whether you have a small cube of ice or whether you have a big glacier. It's always going to melt at 0 degrees. So these are all things that do not depend on the amount. These are all intensive properties. Extensive properties are all things that do depend on the amount. Okay, so it does depend on the amount. So if you have more of something, you're going to have a bigger mass. If you have more of something, you're going to have a bigger volume. The shape is going to depend on how much you have. The length is going to depend on how much you have. Okay? So that's an option for you to have done on page 55, but totally optional. You can check with your answer key to see about those ones if you want to, but you don't need to. Circle the best choices for each of the statements below. Is it physical properties or chemical properties or both that describe matter? Can you guys separate yourselves, please? One of you can go sit here, one of you can go sit here, and one of you can go sit there. Okay. One more over. One more over. One more. One more. Okay. Thank you. Okay. What kind of properties describe matter? Chemical properties or physical properties? Physical properties describe matter. Do chemical properties describe matter? If I say baking soda reacts with vinegar, does that describe the baking soda? Yes. So both of them describe matter. All properties describe matter. Do chemical properties or physical properties describe how a substance reacts? Just chemical. Yes, very good. Can physical properties be used to identify substances? So if you were looking to find this pen, would it be helpful to know that this pen is blue? Yes. So physical can be used to identify a substance. If I had a white powder and I put it with vinegar and it reacted, that would be a chemical property. Could that help me identify what that white powder was? Yes. So also, chemical properties can be used to identify substances. If it reacted with vinegar, you might likely have baking soda. Absolutely. Do we want to go through these last ones or do we feel okay? You want to go through them? Okay, let's go through them. Odorless, oxygen is odorless and colorless, not chemical-less. Is that chemical or physical? Physical. Copper turns green when exposed to the environment. Chemical, because that green is a new substance. A piece of metal is magnetic. Physical, no new substance. The density of water is 1 gram per cubic centimeter. Physical. Diamonds are very hard. Physical. The tree is 8 meters high. Physical. Sodium reacts easily with other elements. Chemical, because it's reacting. Copper conducts electricity. That's physical because you don't have a new substance. The wires in your wall don't turn into something else when you run electricity through them. Otherwise, that would be inconvenient, wouldn't it, if their wires disappeared and turned into something new? Water is a liquid at room temperature. Physical. The mass of some sodium chloride is 30 grams. Physical. Gold is non-flammable. That one's actually chemical because it tells you about its reactivity or its lack of reactivity. Okay? And if it's talking about its reactivity, then it's chemical. Alka-Seltzer tablets react with water to produce gas. We produced a gas and that reacted, so that's chemical. The color of the ball is red. Physical. Iron reacts with oxygen and forms rust. Chemical. The boiling point of water is 100 degrees Celsius. Physical, because we're looking at boiling. That's just a physical change of state. Baking soda reacts with vinegar. Chemical. Gas is flammable. Chemical, because it's talking about how it burns. A burning is a reaction, so chemical. Oxygen is a gas at room temperature. That is physical, because it's just talking about its state. Argon is not very reactive. That's going to be chemical because it talks about its lack of reactivity. Nitrogen is a colorless gas. Physical. The silver spoons tarnished and turned dark. That's chemical. We ended up with a new substance, that dark stuff. A piece of metal is magnetic. Physical, because it doesn't change into anything if it's attracted to a magnet. A student's shirt suddenly bursts into flame. That's disturbing, but chemical, yes. Why? I don't know. That's a crazy one, isn't it? A copper roof tarnishes and turns green. I think we saw that one before, didn't we? That is chemical because we have our new substance there. I'm going to let you go through on your own and decide if things are intensive or extensive if you want to. You don't have to, okay? So now what we're going to do is we're going to go back, because last day we looked at water melting. We looked at a video of that. Today, I thought it might be nice if we looked at how things boil and what it looks like when things boil. And Tyler DeWitt is going to help us out with that. So we are on page 46. Okay, 46. So we are looking at boiling or evaporation or vaporization. That's all going from liquid to gas. Page 46. Yeah, we're going to watch a little video here. There we go. Elliot.
Here's one of the biggest things that people don't understand in chemistry. Keep this in mind. When a liquid boils or evaporates to become a gas, the molecules don't come apart. So let's talk a little bit about liquids, evaporation, boiling, and molecules. So here is a very tiny glass of water. Well, it's a tiny glass of water that we've zoomed in zillions and zillions of times so we can see what makes it up. And what we see is that this glass of water is made of all of these water molecules. One oxygen atom connected to two hydrogen atoms. That's why we call it H2O. So our glass here contains lots of molecules of liquid water. Let's now make some steam, some gas water. What we're going to do is we're going to heat up this liquid water. And as we heat it up, the molecules in it are going to start moving faster and faster and faster until some of them are moving so fast that zoom, they can jump, shoom, right out of the liquid water, enter the air above that liquid, and start flying around. Now, these guys up here are molecules of steam, also known as gas water. So here's the main point. When they're liquid water, the molecules, H2O, are packed really close together. When they're gas water, or steam, they're still molecules of water, one oxygen and two hydrogens. It's just that now they're not as densely packed and they're flying around in the air above the liquid. Here is the mistake that so many people make and that I don't want you to make. This, as we said, is the way that water does evaporate. Here's the mistake that people make. Here is another glass of water. So many people think that when water molecules become gas, that they have to break apart, that the atoms that make up those molecules split apart from each other, And that's the only way that the liquid water can become gas or steam. So we have these molecules here, and they have to rip these atoms apart. And so that if we were to zoom in and look at steam, we wouldn't see water molecules, but we'd see all of these pieces of the molecules, all these atoms ripped apart. This is wrong. Here's the big red X. I don't want you to make that mistake. On the other hand, here is the right way that boiling or evaporation happens. The molecules look just the same in gas as they do in liquid. They do not, big red X, they do not split apart into the atoms that make them up. Same in liquid, same in gas. Okay, now this isn't just true for water. This is true for anything, for any liquid that can evaporate or boil to become a gas. So here I have a tiny amount of gasoline. The molecules look like this. 8 carbon atoms surrounded by 18 hydrogens. And then here I have some alcohol, a carbon with a bunch of hydrogens, and then an oxygen. Now, alcohol and gasoline can both evaporate. If you're like me, you love the smell of gasoline, which is like those vapors that you get when you're filling up your car.
Okay, I find that really weird, but okay.
I love it. So you know firsthand that gasoline can evaporate and become a gas. Here's the point though. Here is the wrong way to think about evaporation. If a gasoline molecule looks like this, the wrong way to think about it is that these molecules would come apart into the pieces and into the individual atoms. And the same thing here with the alcohol. This is wrong. These molecules here have split apart into atoms and pieces of molecules. On the other hand, the right way to think about this is that both the alcohol and the gasoline molecules just nicely lift out of the liquid when they turn from liquid to gas.
So those molecules stay intact. They just separate from one another. That's it. No breaking apart.
This is what the liquid would look like. The molecules are all tightly packed together, and here's what the gas would look like. The same molecules, they're just floating around in the air and they're further apart. So once again, don't make that mistake. Always remember that when a liquid boils or evaporates to become a gas, the molecules don't come apart.
Okay, and we're going to leave that there, and we're going to make sure that we didn't miss anything. So a molecule is a type of particle. So let's label, this is a water molecule. That's a water molecule. What are molecules made of? Molecules are made of atoms. So a molecule is a type of particle. An atom is another type of particle. How many atoms are in a water molecule? 3. Molecules are always made of 2 or more atoms. What types of elements are hydrogen and oxygen? And when we are asked about a type of element, we're usually looking for metal and non-metal. So we're looking for metal or non-metal. And are hydrogen and oxygen metals? No. So if you can say, okay, it's not like zinc or iron or things that I know are metals, so those must be non-metals. And in fact, molecules are always made of non-metal elements. There's no metals in molecules. No metals allowed. Okay, so this is what Tyler showed us. He showed us that when things boil, the water molecules stay intact. Do you guys know the word intact? What does intact mean? Not broken apart. Now there's a little enriched here. Do you want me to do it now or no? Up to you. Anyone want it? No. Okay. So we're just gonna skip on past that. All right, condensation. So we're on our next page now. Condensation. What state are we going from and what state are we going to when we condense? We're going from gas to liquid. And I don't think I have a really good animation for this one, but we do have a simple distillation apparatus, and we're going to watch a video of that, and then we'll take a look at this little diagram here. Okay, so we're going to watch how something might be distilled. Make that bigger. Okay, so you can see we have a flask, and underneath it, what's this thing called underneath it? Do you guys recognize that? That thing underneath the flask? That's a Bunsen burner. So what are we going to do with this flask? We're going to heat it. Yes, absolutely. Okay, and can you imagine that in here, maybe we have some salt water? Okay, so we're going to heat it, and here we go.
When performing a distillation, first the condenser is filled with cold running water. Next,
so this condenser tube, it's actually a double tube. It's got glass on the outside and it's got glass on the inside. So it's actually like a tube within a tube. And through the outside portion of the tube, they actually run cold water. So there's cold water all along the outside of the tube. There is a passage, though, right through the middle where anything that comes up here can flow down and drip through and get condensed as it comes into contact with that cold water.
heat is applied to the mixture which is to be distilled. The mixture is heated until it boils, and the hot vapors will travel up the distillation head. Measuring the temperature of the vapors helps us to identify the liquid being distilled and will help to confirm its purity. If the vapors are pure, they will have a constant temperature equal to the boiling point of the liquid being distilled. As the vapors travel into the condenser, they will be cooled and will liquefy. The liquid droplets, called the distillate, run down the condenser and are collected in a receiving flask. A liquid can be easily separated from non-volatile contaminants by using a simple distillation apparatus such as this one.
So when they say a liquid can be separated from something non-volatile, what that means is if you have salt water, the water is going to boil. Is salt going to boil at 100 degrees Celsius? No, so the salt's just going to stay behind and you'll be left with the salt in the flask.
Since the non-volatile components in the distillation flask will not evaporate, the vapors and the resulting condensate will be pure.
Okay, and that's distillation. And now we're going to look at going from aqueous to solid. Now, this would be like when you have salt water and the water evaporates. What are you going to be left with when the water evaporates? Salt. So this is going from aqueous to solid, and this is called, if anyone is interested, this is called recrystallization. That's a huge word. So if we have salt dissolved in water, what state of matter is that? That is aqueous. So what we would do is we would write NaCl, which is the formula for salt, and in brackets beside it, we would write AQ. Now, once all the all the water has evaporated, we are just left with solid salt. So what would we put up in our second set of brackets beside the sodium chloride? S. We start with salt. We finish with salt. So is that a chemical or a physical change? We started with salt, we finished with salt. That's a physical change. All right, let's watch the little video of how that works.
So here's the dish of water, and if we look very closely, the water molecules are evaporating, and as they evaporate, the concentration of the sodium and chloride ions increases, and the charges bring them closer together, and the attractions hold them together, and they recrystallize as salt.
Does that look kind of like the opposite of what happened last week when we took the salt crystal apart when it was dissolving? Okay, so yeah, exactly the opposite of what happened there. All right. And then there's just, if you want, there's a little picture of it, and just what the video was talking about here. We don't need to go through that though. Now, solid, oh, this is wrong. This should not say solid to liquid. This should say solid to gas. Does yours say solid to liquid? Or does it say solid to gas? It says solid to liquid. Okay, so I need to fix this. Because solid to liquid would be melting, but solid to gas is called sublimation. So this is on page 50 now, page 50. Oh, what's happening here? And this only happens with certain things, but this is like the dry ice. What substance is dry ice made of? Dry ice, it's made of a gas that has deposited and it is now a solid. What gas is it that's become solid? Anyone? Carbon dioxide, yes. Anyone know the formula for carbon dioxide? CO2. Di means two. That's where that two comes from. So you can see we've got carbon dioxide molecules, and just like when something evaporates or boils, the molecules are closely packed. And now the molecules are separated. But did we break the molecules apart? Or did the molecules stay intact? Yeah, molecules are intact. So if we were to write what's happening here, we would write CO2. We started as a solid. We still have CO2, and we finish as a gas. But the molecules haven't changed at all. The molecules are the same as before, so that's why it's a physical process. And I've got all of these written as liquids. These should all be gases. So let's go fix this right now. Down in here, this should say sublimation, solid goes to gas, and deposition, gas goes to solid. Fix. And we're going to go look at the sublimation of iodine. Iodine is another substance, like carbon dioxide, that goes straight from solid to gas rather than melting. So let's go take a look at an experiment that they did with iodine, which is a beautiful purple crystal. Okay, so those are iodine crystals on the outside of that flask. At room temperature, elemental iodine is a black, bluish solid. So they're heating it, and it's going straight from solid to gas, and that gas is this beautiful purple color. Iodine got its name from the Greek word, whatever that was. So they're putting a flask that contains ice up here. Why are they putting ice in that? To cool it down. Because when we heat the iodine, it turns from solid to gas. When we cool it, it's going to turn from gas to solid. Beautiful iodine crystals out of line. Okay. So, I don't know what this one is about. I think we're going to skip it because it's 13 minutes and that sounds like a lot of time. All right. So what I'm going to get you to do right now is the following. Which is page 51. And then once you finish page 51, I'm going to figure out what other page I would like you to do on top of that. A little more stuff on chemical and physical changes. And then we're almost ready to move on to our periodic table. Okay. The periodic table? Perhaps. We'll see how far we get. Yes. Oh, the re-quiz. I would like the re-quiz. Would we like it tomorrow or Wednesday? Wednesday? Okay, so the re-quiz on models of the atoms will be on Wednesday. Thank you for asking. I'd forgotten about that. Oh, that's what we're gonna do. Hi. Yeah. Folks, when you're finished 51, 56, okay? Yes. If anyone missed showing me their homework at the beginning of class and would like to come and show me their homework right now, you can do so.
Yo, you literally said it. 52, right? 52.
It was 52, 53, and 55. Perfect, thank you. Okay. Yeah. 52, 53, and 55. Yay, thank you, June. Nice. Hello. Hello. Yes, thank you so much. There you are. Thank you. Lucas? Lucas, you wanted to show me your homework? Lynn, do you have your homework? Oh, you showed it to you did. Never mind. I don't know what's wrong with me. I'm looking at the wrong name.
I don't remember what
52.
52. Did I do that actually? Wait, 52.
52, 53, 55. Yay.
Oh, sure. Step on your foot? Not bad.
Whoa. 52, 53, 50. Yay. Thank you.
You're welcome.
Hi, Samuel. Thank you. Okay, friends. Most of you are almost done. So we're going to leave the rest up for homework and we're going to go to page 57. 57. So the key thing here, we are looking at these things called particle diagrams, which means that we're looking at the particles. If you get new and different particles, if you have a chemical change, you'll get new particles. The atoms will rearrange. But if it's physical, there's going to be no new particles. Okay, so what you're going to do, and this is the last thing for today, is you're going to take a look at this and you're going to say, when I take these squares, which are particles, and these circles, which are particles, and they undergo this process here, was this a chemical change or a physical change? Do we have new particles or are they the same particles as before? These are the same particles. So was that chemical or physical? Physical. Okay, we're not going to do part 2 today. We'll talk about that next day. Okay, so just part 1, just chemical or physical. You're going to take a look at this one and you're going to say, I started with little black circles and I started with little white circles and I finished with these Mickey Mouse-like looking particles, where now the white particles are attached to black particles. Do we have new particles here? So we started with this and that, and we finished with that. That is a new particle. We have no Mickey Mouses, no Mickeys, no Mickeys. Now we have Mickeys. We have Mickey Mouses. So we have new particles. If we have new particles, was that chemical or was that physical? Chemical. Do you think you'd be able to try the rest of them on your own, or do you want to do a couple more together? Couple more together? Okay. We have, in this first one, we have squares and we have triangles. At the end, after we have squares and we have triangles, were there any new particles? No new particles. So that's going to be physical. Why are we packing up? We still have 5 minutes left. Okay. Actually, we're going to go and we're going to do, what are we going to do next? Let's go down to H. we have these red ones. Are you looking? We have these red ones. We have the one that's black with 4 white things attached. 1, 2, 3, 4. Is that what we have on the other side of the arrow? Do we still have the little double red things? No, now we have a black thing with 2 red things. Do we have new particles? New particles. Is that chemical or physical? Chemical. All right, so you're going to add page 57 on to your homework. There's not very many left. We did most of them already. Okay, so you're going to add on page 57. So now it is what? I can't remember what we had before. $56. 51, 56, 57. There you go. Would you like it for the rest of the day? Right? For the rest of the day.
I can
Okay.
finish the whole thing.
Yeah.
Do you need me to show it to you?
I'll just check you off.
Because
Are
I
you feeling good about it now?
Yeah, I'm feeling a bit better about it.
Okay, good.
It's like a big well, I'll just tell you.
Okay.
Iceland.
I gotta get the homework.
Okay. You want to get this stuff. Awesome. Thank you. Lauren. Thank you so much.
What for homework?
We're in 51.
Level 4?
Oh.
Oh wait, 52, right?
Oh, yeah. Yay, thank you, Peyton.
Yeah.
I probably didn't.